Thermite reactions. They are exciting reactions that release vast amounts of energy in the forms of heat and light. Thermite reactions burn above 2,200 degrees Celsius, and to put that in perspective, the sun's temperature at the surface is around 5,500 degrees Celsius. This reaction is exothermic, releasing approximately 850 kilojoules of energy. Due to this, there are various diagrams showing how the enthalpy of the reaction changes in order to help explain the reaction. Other ways of explaining the reaction are in terms of the products and reactants, and also looking at bond strength and the activity series of metals. One of the main problems with representations is that since they are often simplified, they might miss out on key details that lead to misinterpretations and false beliefs. So we can understand what the issues are with a few different representations, first we are going to look at how the thermite reaction works, particularly in terms of forces, energy, and matter. This reaction is a redox reaction as well as a single displacement reaction. So what is a redox reaction? A redox reaction is a chemical reaction between two species involving the transfer of electrons from one species to another. The species being reduced gains electrons and is called the oxidizing agent. The species being oxidized loses electrons and is called the reducing agent. In the case of thermite reaction, the iron atoms are being reduced as they are gaining electrons. So the iron atoms are the oxidizing agent. The aluminium atoms being oxidized as they are losing electrons, so the aluminium atoms are the reducing agent. When a chemical reaction takes place, energy is either absorbed or released. When the bonds of the reactants are broken, energy is absorbed. This process is endothermic. When the bonds of the reactants are formed, energy is released. This is an exothermic process. There are also forces involved, such as the ionic bond strength in Fe2O3 and Al2O3. The activity series means that metals higher up in the series displace metals lower in the series, but the reaction still requires an initial input of energy to break the original bonds. Another force in this reaction is the expanding of molecules surrounding, mainly gases, due to their increase in temperature. So how do we go about setting up and demonstrating this reaction safely? First things first, the thermite reaction is quite dangerous and proper safety precautions must be taken. Ensure that the area is well ventilated as smoke is generated and we don't want to set off any fire alarms. A lot of heat is produced in the reaction, so ensure that no flammables are nearby and do not stare at the reaction as harmful ultraviolet rays are given off. So what do we need to set up the reaction? We need the thermite mixture. In the setup, we have the thermite mixture suspended above the beaker of water and sand, sitting in a piece of filter paper. Upon igniting the mixture, the reaction will start and the products will fall into the beaker. The water in the beaker is used for cooling the reactants. However, water might not be the best coolant, as the heat of the reactants is hot enough to cause the water to instantaneously be turned to steam, and can potentially spill molten iron everywhere. Sand is also in the beaker to allow the iron to cool. To begin the reaction, we need an ignition source. We have previously stated that the reaction requires a large activation energy, and as such, we need a catalyst to start the reaction. Possible ignition sources include magnesium strip, potassium permanganate powder, something that gives off enough heat for the reaction to start, like a common sparkler. After we begin the reaction, there is enough energy given off to sustain the reaction, and as such the reaction is spontaneous. Here is a video showing the process of conducting a thermite reaction.
Many chemical reactions are exothermic, but none quite like the thermite reaction. Here we have a piece of filter paper which we're going to fold into a cone. We're going to place a mixture of aluminum and iron oxide into the cone. We're also going to add some thermite starting mixture. This is a powdered material which helps the oxidation reaction. We're going to place that then in a hole in this container of sand. I'm then going to place a piece of magnesium ribbon down into the mixture and move the explosion shield into place before we light the magnesium fuse. Now we can take a look at the molten metal by carefully lifting it out of the sand. This white-hot iron is encased in a crucible of glass that has been made by melting the sand.
So what we just saw was a video of a thermite reaction. See that the reaction was quite spectacular, with energy given off in terms of heat and light. The reaction is started by the introduction of heat into the mixture, as heat can be seen as the energy required to break the bonds and start the reaction. We see that the iron oxide is reduced, turning into both liquid iron and solid iron depending on the temperature. The liquid iron cools in the sand mixture, with sand forming glass casing around the iron. Now that you understand how the thermite reaction works, let's take a look at some representations. While this graph shows the change in energy and release of energy, it does not show the energy required to break the bonds. The fact the graph uses colour is useful in holding attention. Also, the graph shows how matter changes state, but it does not show how forces are involved. This provides a way of visualizing the energy inputs and outputs to illustrate the endo or exothermic components. Here we can see the thermite reaction and how the aluminium atoms displace iron and transfer 6 electrons, 3 to each atom of iron. However, this diagram highlights the reactions in terms of matter. It does not aid well in the understanding for how energy and forces are involved in the reaction. However, some understanding of forces can be seen by the fact that the atoms stay together as a molecule, but this is not clearly depicted.
So here we have in this reaction, we have aluminum and iron 3 oxide, which we more commonly refer to as rust. And what they're going to do, as you see, is produce aluminum oxide and iron. Now notice the general pattern in this particular chemical reaction. We classify these types of reactions as single displacement reactions, and there's an identifiable pattern here that you can see. And we can almost picture this like puzzle pieces. Certain puzzle pieces will fit together, others won't. And we say that in these types of reactions that like displaces or replaces like. And in fact, you can see this in this particular reaction. So if we look back at our example, you can see that we have two metals. One metal is by itself, initially that's the aluminum powder, and one metal is in a compound, and that is the iron that's in the iron 3 oxide. And you'll notice over the course of this reaction what happens. The metal displaces or replaces the metal, that is the aluminum, replaces the iron that's in the compound when it's bound with oxygen, and produces an aluminum oxide and iron. And so we see here that the metal displaces or replaces the metal. And we refer to this type of reaction as a single displacement reaction. The metal that is by itself will replace the metal that is in a metallic compound to produce a new metallic compound and a new metal that is by itself.
Video shows how matter displaces each other, however, could lead to some belief that this is not a redox reaction but a single displacement reaction when it's actually both. It does not show how energy is involved in the breaking of the bonds or that energy is involved at all. However, it does show that a force holds the atoms together using the simple analogy of jigsaw pieces as atoms.
So at our dance, we find in the center of the dance floor iron and oxygen. And things are going well. They're dancing and getting along great, but oxygen knows that there are some other metals that it would just make a better couple with. And so into the room walks aluminum. Oxygen sees aluminum and just knows they will make a better pairing than oxygen and iron. So unfortunately, iron is left to dance by itself, and oxygen now pairs up with aluminum. Now, how did oxygen know that it would make a better partner with aluminum than iron? Well, that's where the activity series comes in. You see, iron is below aluminum on the activity series. And the way that the activity series works is that any metal above another metal will displace it from a compound. So you can see aluminum is above iron. So given that opportunity in which we have aluminum reacting with a compound that contains iron, aluminum will displace iron, and that single displacement reaction will occur.
This shows how there is a force that is stronger pulling between aluminium and oxygen compared to iron and oxygen. It does not show how energy is required to initiate this response, but illustrates the matter as cartoon characters, allowing a visualization of the reaction.